I started the recording. Seems like some of the students are missing. Hopefully, we're gonna watch the video lecture. Alright, everybody can see it, right? Let me open the lecture page. So, what we're seeing here is the exam one review. Because remember, when is the exam? Tuesday next week, right? Tuesday next week. Okay. So, what is the syllabus for this exam? Basically, module 1, 2, and 3, right? The new module that I started. If I have time, I'll talk a little bit more about that. There are homeworks for that which I'll upload. I guess like today I won't be bothering you with that. I mean, just let me focus on this one first, the exam on review. All right, so it has like few questions here, as you can see. At some point, we're going to talk about those questions. Okay, but before that, let's quickly review the theory that whatever we learned so far. Okay, I want everyone to be ready with pen and paper. Okay, because I'm gonna be starting the class note now. Ready? All right, exam on review. So first thing first, the theory review that I'll be doing next. What did happen in the first week here? We did learn about some units, remember? So let's deal with that. Some basic units. So starting with heat rate. I'm writing what we're doing now, and you'll try to write the units by yourself. Okay. Obviously, I'm gonna write it a little later. So then heat flux, right? Conductivity, convection coefficient. We're a little fast on writing because we got to cover so much. Okay, not only that, what I'm doing now, along with that, these problems as well. So much thing to cover. Then cylindrical and Cartesian coordinate system, right? Okay. Then we also learn heat rate per unit length. Okay. Density, specific heat at constant pressure. Emissivity, absorptivity, reflectivity, transmissivity, Stefan Boltzmann constant. All right. So many things. So you'd like to start writing this way. So like the heat, we know the heat usually refers by Q, right? The capital Q is in joule. The heat rate is small q, is joule per second or watt, right? Heat flux is what? What is the unit for heat flux that we use? Anyone? Q double prime, right? Watt per meter square. What is the unit of conductivity that we use? watt per meter Kelvin, which is K, right? What is the convection coefficient? Quite a bit of silent class, right? H, right? What is the unit for H? Anyone? Okay. What about others? Only Steve? No one remember? All right. I know, Logan, you remember, right? Everything? All right. So cylindrical and Cartesian coordinate system, right? On that one, you have X, Y, Z, right? And you have in cylindrical, you guys remember R, theta, and Z? What is the heat rate per unit length? What is the unit that we use? Single prime, and the unit is watt per meter. Why we are using this in a cylinder or in a 2D in a cylinder, right? So you use it in cylinder. Density is rho. Everybody know density, so I don't want to ask this. Specific heat. What is the symbol we use? Cp, Cb, or C, right? So usually we use Cp. You guys remember that? Cp means what? Specific heat at constant pressure, right? Cp means specific heat at constant volume, and C means like it is like constant specific heat for constant pressure or volume. C usually used for why? Cp or Cv usually used for gas. C usually used for liquid or solid. Why? If the liquid is considered as incompressible, right? The pressure doesn't have that much of effect. Does it make sense? In that case, but it does have different values though. That's the exception, okay? But for solid, definitely one value of C for sure, right? Constant pressure, at constant pressure. P refers to constant pressure. Okay, what is the unit of Cp? Anyone? Yes, joule per kilogram Kelvin. Very good, thank you. It's not watt, don't get confused with that, right? All right, what is emissivity? Epsilon. What is the unit of epsilon? No unit, right? What could be the value for epsilon?
Between 0
to 100% or 0 to 1, right? Absorptivity, what is the symbol for that? Alpha. Reflectivity, rho. Now don't get confused with this rho with the density rho, right, Diffu? Diffu, remember everything? No, you missed some initial classes. We learn everything in the initial few classes. So we have all the lectures are in record, okay? So maybe you would like to watch some of the video lecture, okay? Diffu? That would be my suggestions, okay? Because this is like week 5, day 2. So how many classes we did after the, I mean, considering the first class we didn't do, right? Like no new material. So we had like 8 classes happened here, right? We are here, how many hours? Think about it. So almost more than 9 hours, right? So we had learned so many things within 9 hours, right? And straight at 9 hours, I'm giving you info. It's not like you are doing math or something, right? So we are doing a summary of almost not 9 hours. Last class you can ignore. So like around 7 to 7.5 hours of summary that I'm doing. So please be attentive. So many things I'm going to be covering, okay? So to give you an idea what is going on in general. All right. So absorptivity, reflectivity, transmissivity. What is the symbol that we use for transmissivity? All right, sigma, right? So then Stefan-Boltzmann constant. And by the way, all those things like absorptivity, reflectivity, transmissivity does have the same value. Just like 0 to 1, 0 to 1, 0 to 1, right? Now, Stefan-Boltzmann constant, what is the symbol that we use for that? Sigma. Anyone remember the value? 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4. Remember that? I'll admit you guys are doing good. Okay, perfect. All right, so moving on. So next, let's move to the basic question for conduction, convection, and radiation. Okay, as a review. So we have conduction. Let me write the conduction first, convection and radiation all side by side. And radiation, right? Radiation. All right. So for conduction, if we are dealing with 1D case, 1D, no heat generation, steady state, right? And the simplest form of equation that we can write, which is Q minus K A del T over L. Everybody remember that? We did our first math problem using this equation for the basement floor heat rate. How do you remember that equation, right? The first math problem we did here in class, right? So that is the simplest case ever possible, like the basement floor where the one temperature is known, another temperature we found, where the Q was given, or maybe the Q that we found, both temperatures are given, I forgot now, right? The K value was given, right? And the area you found it. And this L, what is this L? Anyone remember? That's the thickness, right? Delta is the change of temperature. Obviously, I don't have time to write the detail of everything. I'll just simply put the highlight of those equations. Now, there are other equations for conduction we learned as well, right? So this same equation, by the way, before I do that, let me give you the heat flux equation, okay? And heat flux, you just simply take out the A, okay? And the other form of equation that I was talking, which is heat flux minus K, del T del X. Now tell me something. If I'm going to write the heat flux equation minus K del T, what does it really mean? Did I use this symbol before? Probably not, right? But I did use this one for sure, I remember, which is del X I del Y J del Z K. Did I use that? All right, so you understand that symbol they call delta. And delta is referring when we have more than one axis, right? Remember so far? Okay, why do you have the partial and why do you have the ordinary? When you have partial, that means it's 3D. When you have ordinary, that means it's 1D. Okay? Differential equation, I'm saying. See? Any question with the conduction? The conduction equation is called Fourier's law. You know that, right? It's a Fourier's law. Now, there is another law for convection that equation is called Newton's law of cooling. You heard about that before? Newton's law of cooling? Maybe not. So that is Q. Everybody may want to take the class note. I know it could be silly to some of you, but still you never know. It could be a good practice for you. This del T. Now what is this del T? It depends on which two temperature you are referring for convection, right? You know that. As an example, if air is going on the top of the surface, the top of you, top of the floor, top of this table, whatever it is, like this two temperature difference, it's referring the surface temperature and the air temperature. You know that, right? What is this H? We have seen it's the convection coefficient. We know the unit. Now, up until this point, we don't know how to find the value of the H. Every time, what happens, Chelsea? The value of the H was given to you, right? Mm-hmm. So you don't have to worry about how to find the H or whatever. Okay, but just to understand, this H can vary depending on the situation. Like if you are dealing with a forced convection or if you're dealing with a free convection. You guys remember those, right? Forced and free. If I'm going to bring a fan here, just turn it on, it would be forced, right? Okay, so that's the H convection. Just trying to wrap up as quickly as I can. Bless you. So then H del T, the A is missing if you have a Q double prime, right? The radiation equation, everybody remember the radiation, that one is the most trickiest one. On the radiation equation, say like you have a solid surface and you have a dome on the top of it, and the surrounding temperature is the dome, and the solid surface temperature Ts, and you have say like air blowing inside the room. Okay, this is your situation. Now the Q equation, I don't know if you remember, again Q is the heat rate, you know that. So this Q radiation, The Q equation would be epsilon sigma A Ts to the power 4 T surrounding to the power 4. You remember that equation? That's the radiation equation. I know you have implemented this thing in different homeworks. You are literally master on this right now. Everyone feeling very comfortable with up to this point? That is good. Everyone needs to be very comfortable to this point. One student is missing all the time. Did you guys ever see Madeline? You know Madeline, right?
I've seen her like once this semester.
I did once as well. I don't know. I don't know the future of the exam. I'm just wondering because the exam is coming. Anyway, let's move on, okay? Oh, by the way, this del T, you know, this could be like T1 minus T2, right, divided by L, multiplied by this Ka.
I thought it was T2 minus T1.
Yeah, it is absolutely because I didn't write the minus. That's why, you know what I'm saying, Chelsea.
Yeah.
That's why I wrote T1 minus T2.
Okay.
It's a shortcut. Don't worry about that. Okay. Now let's focus on the next agenda. Like on module 2. What did you learn? What is the main agenda on module 2? You remember? Is the energy balance, like energy balance, the relationship of thermal heat transfer, right? Energy balance at surface. Remember you did in math, in homework 1 last problem, right? Then in homework you did 2 problems, right? Energy balance at surface. So you'll be definitely expecting a question like something similar, right? In exam, the energy balance at the surface, because you did like almost how many? 3 in homework, 1 here in class, so 4 problems you did, right? So what I've been, if I've been in position, I've been reviewing all 4 of them, right? I think I uploaded all the homework solutions as well, right? In the red space. So the solution should be handy to you. If not, then I'm gonna send upload it right away for them for the most recent homework too. The homework 2, the second part, that one I probably didn't yet. But one and 2, I believe I did, right? The solution manual, I did, right? Steve is, yeah, and nodding. So definitely I did. So there are 2 solutions. There are 2 solutions for you to do review, right? I mean, now when I'm saying all of this, the surface energy balance, that the topic that I'm going to cover now, we did 4 problems. I'll do this review of 4 problems before coming to the exam. Okay, those 4 problems. So because you'll be seeing something similar here, right? Surface energy balance. So now that's the intro, right? About the surface energy balance. What is surface energy balance? I always like to use this example, right? If we have heat inside, that means high temperature. So high temperature inside this block, right? So at the surface, you'll be expecting you'll lose some heat on the here as convection, and you'll lose some heat from here to here in surroundings as radiation. You know that, right? Everyone remember? So now, question is, I have a question. Let's see the answer. So heat is losing here from this surface to that surface that I said. Does it mean heat will not gonna get loose in any other surface? Only the surrounding means only the ceiling and the sidewall, or heat will gonna lose in other surfaces as well? What will happen to me if that surface can see me? Do you think that surface is gonna lose the heat or gain the heat? It depends. What is the temperature there? I know my temperature 98. This surface temperature is like more than 98, say like 100. Then definitely this will gonna give me heat. As long as this surface can see me. You understand? That's the important thing about the radiation, okay? This will only gonna give me heat, this surface only I'm talking, as long as it can see me. If it can't see me, it will not gonna give me any heat. So that's the interesting part of the radiation, okay? So I'm just saying like, so this surface, whatever it can see around, as I was saying, like, if it sees the ceiling, it is gonna give it heat. If it sees the sidewall, it will gonna give it heat. If it can't see the floor, it will not gonna give it heat. It make sense? Everyone understand? So that's the concept of the radiation, okay? And I was just saying like, okay, again, the surface energy balance at the surface, you have the conduction, which could be equal to convection and radiation. Everyone understand this? All right. So that's my second topic.
Also, in terms of solution manuals, you only have it up for one.
Just one. So I'll upload the other twos as well. Okay. So I'll upload I'll upload the other two. Okay. Yeah, other two, and then I gotta finish the grading as well. Yeah.
Are we supposed to go over the problems for homework 3 today? Because you want to cover those.
Oh, the homework 3 games.
Yeah.
Yeah. I have like 3 problems here as a review. I mean, I don't know if I'm gonna get time. If I don't, then I can offer you this, like after this class, in-person help with homework. Okay. That is probably proper use of the time. Okay. All right. So moving on. So the next topic. So surface energy balance we are talking, right? So at the surface, you always draw this dotted line, and you have this conduction, and you have this like convection and radiation, right? So you can write depending on the temperature situation, like say like you have a temperature here Ts, T infinity, and the surroundings is T surrounding. So depending on the temperature situation, you could have like this: if this Ts is higher than T infinity and Ts is higher than T surrounding, right? Then you can write Q conduction equal Q convection plus Q radiation. Now this could be a flux, this could be total rate. I mean, depending on the situation that you are dealing with. And that's kind of the module 1 and 2 review done. Okay, I mean not the math yet, but the theory wise. Any question with that? The module 3 that I'm gonna cover now. Okay, that will gonna take a little bit of time. It was good. Oh, that question. Now I remember that homework 2 part 2 is really extensive. How far you guys have done it then?
I attempted problem 1 and hit a wall very quickly. So
I understand. How many of you tried this homework 2 part 2? Some of you struggle. How many of you struggle? I mean, Matt obviously expressed his view. What about Logan? Struggling? Mitch struggling? Well, a majority of the class is struggling the way I'm seeing, like homework 3, right? Or homework 2 part 2, like, you know. I'm thinking. All right, how to
do problem 1 and like was problem 1 the hardest? 1 and 4.
1 is the hardest one. I'll try to take a look on this after this review. I guess that could be one best way to deal this class as well, right? Let me do that. Okay, moving on. Okay, let me quickly finish this module 3 review. That could be helpful as well. Okay, so module 3. So everybody remember the heat diffusion equation? So heat diffusion equation has, like, you know, Cartesian and cylindrical, these 2 different formats, right? So let me start writing the Cartesian. Okay, and there is this cylindrical as well. I have a cylindrical image. I'm not seeing it now. So the cylindrical one would be I hope I'm doing it correctly. I don't recall exactly the cylindrical d-phi. All right. I want everybody to be very comfortable with these two equations, okay? The thing, once you have those equations, you're going to simply apply those boundary conditions, apply the assumptions. I mean, the assumptions could be like, 1D steady state and Q dot equal to 0, okay? And constant property. There are like 4 assumptions that can come up here. Right, Mitch? Remember? 1D, Q equal to 0, what else? Steady state and constant properties. Always remember these 4, right? These four assumptions dictate the problem. Okay. So if you have a steady state, obviously the right one is going to go away. If you have a 1D, then the other 2 is going to go away, right? The Y and Z in Cartesian. If you have Q dot equal to 0, then Q dot is going to go away from this equation. Then this equation could be very simpler, just the way I wrote in last class, if you remember. So this 1D steady state Q dot equal to 0 and K constant, this will gonna lead to the equation of this one d by dx K dt dx equals 0, right? So just to give you one form of simplified equation, okay? I don't want to deal with any further, but because we have in class seen what happens in cylindrical coordinates, right? As well, we have seen what happened when we have a non-steady case, right? We found a dt. We have seen what happened when you have a q dot term present, okay? So we have seen all those things in different problems in class. You guys remember? Like a nuclear rod problem we did, right? For cylindrical problem where we find the dt. Is it ring a bell to everyone? So those math problem I would encourage you to review. Now, I'd like to stop here in terms of the theory review. Okay. Now I'd like to move to the homework hints, since like majority of the class needs help on that. Okay. And then I'll come back again here with these 3 problems. If I can get time with these 3 problems, just to give you an idea, those 3 problems are very similar to homework that I'm gonna be giving review one of them, and other 2 are very straightforward of homework 1 and 2. Okay. But still, I can possibly talk a little bit here as well. Or what do you want me to do? Review those 3 problems first and then go to the homework 2 hints. Which one? What the majority wants? This one? Okay. All right. So let me quickly review these 3 problems. Okay. You guys are done with the writing or still need some time? Okay. Let me know when you're done. If you are good? Okay. Just to let you know, the lecture is in record as well, so you have the access of this lecture later on as well. If you're not feeling good, watch the video lecture later on. All right, I'm just copying the same questions here because I have the text over there. Okay, let's read one by one. Okay, David. So few students raised concern. Okay, about homework 2 part 2. David, Matt, Logan, Chelsea. The 4 of you, don't worry, I'm gonna work with you even in person, okay? With the homework 2 things. Okay? If we don't get time. Since some of the students also are done with homework 2 part 2, they want to see like these problems. Okay? You understand? Because this is the priority, the review for the exam. Alright, you understand why I'm doing it, okay? Alright, so moving on. An isothermal chip. Okay, obviously I don't have time to finish all the problems with all those things that I'm doing. I'm gonna give you kind of a hints or guideline how to solve it. Is it okay, Isaac? So instead of solving the whole problem, I'm gonna give you like kind of guidelines how to solve it. Okay, hints kind of a thing. Okay, so you can solve it by yourself. So a isothermal chip, a width of 10 by 20. So they gave you say like 10 by 20 millimeter, right? And 2 millimeter thickness. They gave you 2 millimeter thickness. Mounted on a substrate such that its back surface is well insulated. What does it mean? The back surface well insulated means, anybody remember what means insulated? Well insulated means no heat happened, right? Insulation means no heat happened. That's the assumptions. It should strike on your mind. Okay, so there is no heat at the bottom surface. So how many surfaces it get exposed to for heat then? Not 6, 5 surface, right? Those 4 sides and the top side. You guys agree, right? All right, perfect. So it says here the front surface is exposed to flow of a coolant. So there is a coolant that is flowing, right? With a T infinity, where the T infinity is 10 degrees Celsius. From flexibility consideration, the chip temperature doesn't exceed. So they said like the TS here, it should be less than or equal 90 degrees Celsius, right? If the coolant is air and the corresponding convection coefficient is 150, so they have several parts of the problem. Part A is giving you the H value is 150 watt per meter square Kelvin, and they said is air. So I'm highlighting that air and that 150 value. What is the maximum allowable chip power? So they're asking you what is the Q value. Can you find it, David? Is it a difficult problem? It should be very easy and super easy. It's a very easy problem. Why? Because they gave you 2 things, the temperature wise, the surface temperature and the air temperature. What else? They gave you the H value. Okay.
They gave all the
It will be just the convection, right? Around the sides. Okay, how many sides there? 5 sides. Did they give all the dimensions? So can you find the value of the area A, right, for all the surfaces separately, right? So you're going to have the total A value, right, where you have 5 sides, right? Means there are 5 sides, right? So the top surface is one side, there are 4 more sides on the side. The bottom surface, do you care? No, because it's insulated. They said like, okay, no heat transfer, right, Arlene? Okay, so then there is like 5 surface. You can find the area of the 5 surface, and then you can use which equation again? Convection equation, right?
Yeah.
Which is equal to HA delta T. Does everyone feel confident with this doing this first part of the problem? I'm gonna, as I said, I'm gonna simply write the equation and give you some directions. That's it. So like your Q would be HA del T. Now this del T is obviously Ts minus T infinity, and A should be, I'm not going to solve it though, I'll just say it is 5 exposed surface, right? This little handwriting, overriding. Exposed surface. It is good. Part A done. Part B. Take your time, finish the note. Let me know if you have any questions. Small? It's better? You want to come front, Steve, maybe? There's a seat next to Chelsea. Nobody's sitting here. Good. So first part of the problem done, right? Officially? Good? First part, Matt, you're good? All right. Chelsea, you need some more time to writing? Take your time. All right, perfect. So now second part. If the coolant is dielectric liquid and corresponding convection coefficient is some different value, much higher, what is the maximum allowed Q power? So this, they said, instead of H1, H2 is 2000 watt per meter square Kelvin. How many of you are here gamer? 1, 2. Oh, everybody's gamer. Interesting. Almost everyone. Okay, so you guys use a gaming desktop. So you guys have a transparent thing on the side, and you see like the coolant is. You guys see the coolant, okay? And especially nowadays for graphic cards, they have the extra coolant, right? So I mean that's the dielectric. What I'm trying to say, instead of the conventional laptop next to Mac, right, the desktop, inside the desktop, if you're gonna open the CPU, you will be seeing no coolant. It's just a fact, right? That's the first problem. You understand? The second second problem is where you have coolant, the liquid coolant, the dielectric thing, right? So that thing is much higher H2 value, okay? Because much faster cooling we're going to have it. You see? So it's 2000. Now, the problem itself, does it change at all? No, it is still the same problem. You still have the Q, you still have the H, you still have the delta, you still have the A. Now, instead of H, like I wrote before, you want to write this H2, you want to write H1 here, right? So subscript refers to what we are trying to tell you here. Any question? Everybody can do this problem? Perfect. Take your time, finish the note. Okay, for the third one, it says, if the chip get exposed with very high temperature oven with a 400 degrees Celsius surrounding temperature, then find the radiation heat transfer with the oven when water is used as a coolant. Now use chip power from 1 for this analysis. What does it say? So they said, find the radiation heat transfer with the oven when water is used as a coolant. So this problem completely changed. What it's saying here, say like the same chip I'm drawing. Okay, I have liquid water. Okay, water is flowing on the top of the chip or surrounding chip, right? Matt, you understand the problem? It's a little different. And then it says wall of the oven. Okay, so chip get exposed to very high temperature with 400 degrees surrounding temperature. Say like this surrounding temperature is 400 degrees Celsius. Now, what could be application of that? Like it's really for high temperature. We're talking for electronic chip. What could be application? This is in process industry. This can happen, right? Electronic chip may control a actuator. You know, you guys know what is actuator, right? Still, you know what is actuator, right? So, electronic chip with a PLC programming on may be exposed to the very high temperature, right? Maybe not 400 degrees Celsius, but it could be more than like the regular temperature for sure. So what I'm trying to tell you here, if you have a situation where that electronic chip gets exposed to that high temperature and coolant like water is flowing on the top of the chip, right? All right. So it's like it's submerged chip, right? So in that case, there is the H value for the water that you need to know. Okay, if you have to explore that, there is this Q value, the chip that the amount of power that it produces, you need to know, right, to find the radiation. Okay, if you are considering there is a convection going on. So this problem has several dimensions. As it says here, find the radiation heat transfer. Now, first thing first, you'd like to write the surface energy heat balance, right? So, which is this Q here, right? Chip is equal to, say like this Q convection, this Q radiation. Okay. Now here's the thing: the chip temperature could be more than 400 degrees Celsius, could be way less than 400. Depending on the temperature, either radiation will gonna either go up to the chip or it may come to the chip. Is it clear to everyone? So basically, it's a surface energy balance problem. Okay. Now they tell you this chip, the answer is from problem 1A. So that answer, whatever you found here, you're going to use it here. It makes sense? So then you have this convection plus you have this radiation. They didn't give you the emissivity value. Did they give the emissivity value? So you can, like, some of you may mislead and try to solve the radiation by using this equation here. If you try to do that, you see several problems you're going to face. The first problem is that value is not known, right? You can assume something and able to solve it, but still, there's question mark, right? because that will not gonna may adjust like everything. But there could be a way around if the H value was not given. Does it make sense? H value for the water. If that is not given, then maybe you can find it that way and do the surface energy balance to find the convection. So several ways this problem can happen. Okay, I'm seeing a headlight look to some distance. Okay, this is a typical scenario that I'm presenting here. Okay, let's try to focus. So we do have the cheap power to speed, right? That's the convection. Now, from the surface energy balance, convection equal convection and radiation. You understand that? Okay. So now question is asking what is the radiation. Now you need both the convection and the convection to find the radiation, right? The question is, we have the conduction, right? But do you have the convection? No, not directly. So that is the problem here. So even if we try to do the surface energy balance, we don't have a means. It just says like water is flowing on the top of it, right? It didn't give you the H value. It didn't give you the water temperature, nothing, right? So in that case, when you're trying to do the surface energy balance, it will be difficult. Then you'd like to solve it by doing this equation, the Q rate, the thing that I said the epsilon is unknown. So then the other problem you're going to face. What is the epsilon value? Everyone understand what I'm trying to say? So you're going to do some assumptions either way around, okay? If you want to do the assumptions, usually the epsilon value would be much higher for a chip. Chips are usually in black color, okay? It is close to 1, okay? More than 0.9 for sure, okay? So usually, even Google it also use the 0.9 or something like that. The assumption of Google it for standard chip or the epsilon value. Any question? You're supposed to assume that is the easiest route. Okay. So the second question, everyone is done with question number 1? Matthew, understand question number 1? Okay, so second question. What is the time? I forgot my watch. Okay, maybe I can able to finish the other two within next 10-15 minutes, then I'll still have some time, 15 minutes here in class to talk about the homework, okay? How about that? And then after this class, we'll talk more, okay? All right, so the second problem, it says wall of a oven has a thickness of 430 millimeter and is exposed to a large surrounding and air at the outer surface. The air, so let me start to draw when I'm talking. Sorry. So number 2, let me start to solve it here. So number 2, so you have a wall of an oven with a thickness of 430 millimeter is exposed to large surrounding of air at the outer surface, air and surrounding temperature. You guys know how to draw a surrounding? Do you guys know that? The thing that I just draw is the surrounding, like this L-shaped thing and hatchet line. So that's what people use for surrounding. So that's T surrounding and this T infinity, right? Those two temperatures are known as well. So bless you. So okay, so this one is 15, this one is 17, right? And the surface temperature Ts is given as 110 degrees Celsius. Convection coefficient efficiency, so those values are given as well. So H is given as 60 watt per meter square Kelvin. And then epsilon value is given as 0.95. What is the temperature of the inner surface of the oven if the wall has a thermal conductivity? So the K value is given here as well, 2.6 watt per meter Kelvin. So if this is TS2 and this is TS1, they are asking to find TS1. See if everybody understand the problem. Are you taking the class note? You understand this problem? What you're trying to do here? The inner surface temperature, right? Is the outer surface temperature given? It is. What is that value? 110. That is it. What is the air temperature? What is the surrounding temperature? 17. Is the epsilon and H are given as well, right? So to solve this problem, You want to do what? At surface, at T2 surface, right? You want to do a surface energy balance. If you do a surface energy balance at that surface, you know the conduction should be equal to what? Right? Convection and radiation. Agree? Everybody agree on that? Conduction is equal to convection and radiation, right? At the surface. Chelsea, you agree? So if conduction equal to convection and radiation, let me write it. If this Q conduction equal Q convection plus Q radiation. Now, why I said convection plus radiation? Why? Because of the temperature. Temperature dictates that, right? The surface temperature is way higher, 110 compared to 15 and 17, right? That's why I can claim that, otherwise not. So then there's another problem that I'm facing. I don't have the surface area. If you don't have a surface area, you'd like to do a flux. Very good. See, double line is flux, right? Double inverted comma. It's good, right, so far? Okay, and you understand why I'm doing the flux, right? All right, then here's the thing. So then you got to write this equation minus K. Okay, so T2 minus T1 divided by L. This is my L, by the way, equal H Ts2 minus T infinity plus epsilon sigma Ts2 T surrounding to the power 4. Now here this T1 and T2 can be also written as Ts2 Ts1. So can you solve this equation and find the value of Ts1? Because these values that I'm putting tick mark, all the values are known. Everything is known except the sigma. We know the sigma is 5.67 10 to the power minus 8 watt per meter square Kelvin to the power 4. I think you're good? You're not seeing it properly? How about now?
Yeah, that works.
Thank
Thank you.
you. Is it a difficult problem or no? So far it's straightforward, right? The final one. Take your time. Matt, is it a difficult problem? Very straightforward, right? The main challenge you're gonna face on the third problem, like the one that has something to do with the stuff, the heat equation. Let me know when you guys are done, okay? So I can move to the third one.
You have the exam one will be posted on Workspace as well.
What's up, Jesse?
I just answered my own question.
All right.
No worries.
Okay. All right. Okay. So the third problem, right? Everything's good? The third one? So we are dealing with the third one now. What is the time, Steve?
11:52.
We do have time. The third one will not going to take more than 5-10 minutes. Okay, so a pipe is used to transport the water with an inner radius of 0.04 meter, outer radius of 5 centimeter. Okay, so there is this pipe. Let me draw that pipe. Otherwise, you're going to lose the thought process here. What is going on? Okay, and this pipe does have a thickness. Okay, so they said the inner radius is, what is the inner radius? 4 centimeter, and outer radius is 5 centimeter. They didn't get 4 directly, they get like, okay, 0.4 meter. It's the same thing as. All right, so then they were saying the thermal conductivity of the pipe material is 1.5 watt per meter Kelvin. The inner and outer surface of the pipe maintained at average temperature of 25 and 100. Okay, So let me do those. They said like the thermal conductivity here, K. What is the K value they said? 1.5? Sorry. Meter per Kelvin. What is the inner and outer surface temperature they said? Probably forgot, right? So 25 and 100. Okay, so far these are the things they gave you, right? What else? Obtain, so that's the first part. Obtain a general relation of temperature distribution inside the pipe under steady conditions. Solve differential equation with boundary condition. This is where you may start to trip off, right? So what does it says? So part A, they said obtain what? Heat equation, right? Heat equation under steady state. What else they gave? Did they give any other condition? No. Inside the pipe under steady state. Okay, general equation of the temperature distribution. Oh, temperature distribution inside the pipe. Solve for the differential equation with boundary condition. Oh, so they are asking. Okay, not obtain that at all. They are asking using heat equation. Using heat equation, find the temperature distribution equation for the pipe. You understand that? And you got to apply the boundary condition. What are the boundary condition here? Anyone? What do you think the boundary conditions here, Matt?
It would be 1D probably.
It is definitely 1D you're going to consider. That is one. But the boundary conditions. What are the boundary conditions? Once we have the equation like the, like the equation simplified, the heat equation. K is constant, that is important. But think about the surface temperature inside and outside. Are those changing? No. So those are your boundary conditions. Everybody understand that? So just the same problem that we did in last class. Very similar, but it's a cylindrical coordinate system problem. Last class problem was what? A Cartesian one. So you and I start writing the heat diffusion equation. So like 1 over R dr rk dt dr, and then 1 over r square d dphi k dt dphi d by dz k dt dz plus q dot equal rho cp dt dt. Now, based on some assumptions that you want to do here, right? Some assumptions. What are those assumptions? 1D, steady state, no heat generation, constant K. So this all gonna go away. We're gonna live with this 1 over R d dt R dt dr equal to 0. This K will gonna go away. You understand that, right? Everybody? All right. So I'm gonna give you some equation manual. I want everybody to print it before you come. So I do have equation manual. Let me show you the equation manual. Okay. So where is my equation manual? All right, conduction overall. So this is the equation manual I created for you guys. and I will gonna give you this equation manual, okay, so you can use it. Okay, so you can use it in the exam. I want everybody to print it before you come, okay, in the exam. If you need help on printing, let me know. I'm going to do it for you, but otherwise I would expect you to do that. So what is the benefit of this equation manual? If you have this equation manual, then things will be much more easier, okay. So if you have a situation what we are trying to solve, where you have steady state 1D not heat generation, right, and you have these two temperature known, you guys agree? Is that the situation Matt we have? Exactly that situation, right? So what you want to do, you can use this solution, right? Everybody see that? And use this C1, C2 value, whatever is written here, and use this final thing. Just simply write it. You don't have to solve it. You don't have to solve the differential equation. You can simply use this equation manual. Then life will be much easier, right, Logan? Everybody agree with me? The life is much easier. You don't have to solve the differential equation. You just simply write it. Because I did show you one of the derivations before. I don't want you to. I don't want to show the same thing again and again, because this is the similar way you're gonna find it, like this temperature distribution, right? And then similar way, because the reason I'm saying similar way, because you have 1 over r, when you're gonna do the differentiation, it will be ln r. That's why this ln r came here. But this is the generalized equation, okay, where the C1 and C2s are what? Those are constant, right? So you need to find those C1 and C2 value. How are you gonna find it? By applying these two boundary conditions. One time you're gonna apply what? Like this T1 equal to at r equal to whatever value, then you're gonna apply it here. You're gonna find the value of the C1 and C2 this way. Once you have those, you're gonna simply apply the C1 and C2 value here, and this is the temperature distribution equation that you're gonna get. Everyone understand? So I wanted to write this thing, whatever is here in the equation manual. And if you'd like to understand it more, just do the derivation by yourself. The book does have the derivation. Come to me in my office. I'm going to do the derivation for you. Okay? In class time, I don't have time. If I'm going to start to do this derivation, it'll going to very well take more than 15 to 20 minutes. Okay? Just like in last class. You see, last class just went here like this. I couldn't able to finish anything just after one derivation. It is impossible to do like multiple derivation in every class and finish all the class topics. Everybody's good now? So this equation manual, by the way, again, I'm highlighting that. Harley, tell Mitch, I don't know where he is now. Tell Mitch, like I'll be uploading the equation manual in Brightspace. Get a printout before coming to the exam, okay? This equation manual, I'm putting in Brightspace, okay? After this class, all right? Everybody get a printout. If you need help on printing, let me know. I mean, then I've got to use my account, okay? I try not to print this kind of thing because the dean's office is saying not to print too much, okay? So, but you do have free printing. You can use yours, right? Everybody have free printing, right? Okay, so you can use yours instead of my account. And then they're gonna say what you're doing. Okay, so I'm taking it out. Everybody's clear with no confusion. Okay, so you basically have to use this equation. That's I would like to highlight. And this equation, what is this equation? Heat flux equation, right? How to find this heat flux? Heat flux is, you have this equation, Q equal minus Ka dt dr. Now you see, once you have the T, then basically it's saying here, okay, do this. I'm not going to do the derivation. I'll just show it to you what it's saying here. Do this means you write the whole equation where you have this T1 plus ln of r by r1 divided by ln of r2 by r1. When I was undergrad, I used to do all the derivation by myself. So I'm saying it to those who are really into it or really would like to explore or learn more. Please do that derivation by yourself. When I was undergrad, as I was saying, like I used to do all the derivation by myself. Okay, this is not that difficult to do that derivation, but it just requires a little bit of work. Okay. Anyway, so when you're going to do the derivation, this thing, if you have this constant, this is going to go away, right? So then you're going to come up with this minus k 2 pi l t1 minus t2. Sorry, this minus is going to go away if you have t1 minus t2 and ln of r2 over r1. Now in the problem, you see, that's the assumption they did. They have this T1 inner surface and T2 outer surface. In my problem, what did I do? Ti as T1 and To as T2. Do you guys remember that? Inner and outer surface? Matt, you're good? Is there any question here? Everybody's good? So this, again, I'm emphasizing that this equation manual I'm gonna upload in Brightspace. Okay, please print it out. This will be really helpful to you. Okay. Okay, so the next one is, what if you have a heat generation is there? Okay, so then there are equations as well. Okay, I'm not going to cover that, but I'll gonna, now I guess it's time for me to move to the thing that I was saying. Okay, see equation manual and move to the homework hints. Okay, and the final one, it says here, determine the rate of heat gain, right, per unit length. So again, so for temperature equation and Q equation, you go on equation manual and solve it. Can you do that? You do that, right? David, you good? You can do it, right? All right. So now it's time to deal with the homework hints. Okay, everyone's ready? What time it is now? 10 minutes left. Let's see what I can do within 10 minutes. Take your time. Let me know when you're done so I can move on. Done, everyone? Okay. By the way, if for whatever reason, I mean, you are not able to finish it, okay, the class notes, but you're saying you're done and blah, blah. So you always have the reference here, right? You know, you have the video lecture uploaded after every class in Brightspace. So there's the link for YouTube video lecture with a subtitle over there. So please watch it and deal with that, okay? Just to let you know, you have the source. Now that you don't have the OneNote, that's why I'm saying this, okay? All right, moving on to the homework. So let me see. All right. Is this the homework question? Is this the homework question, like 4 of them? So this is the first one that you're saying, like, Matt, you need some help. Let's try to, I don't have any class after this. I'm going to continue doing this lecture even here, okay? If you are interested, you can stay here until you want, okay? Let's deal with that. So the first problem, it says here, a steam pipe where L is length is given as 30 meter. Mitch, I was saying there is the equation manual I'm going to upload. Please print it. Mitch, you are not there. I was saying, like, I'm going to upload a equation manual. Print it, please, before coming to the exam hall next week, okay? All right, so here it is 30 meter, right? So they gave inner radius. So the inner radius is Ri, given as what, like 5. The outer radius Ro, given as 7. The conductivity K is given as 15. The inner and outer surface of the pipe are maintained at average temperature of, okay, so they gave you the Ti. So 140, right? So they gave you the To. Obtain a general relation for temperature distribution inside the pipe under a steady state condition. Determine the heat loss from the steam pipe. Matt, isn't it the same problem that we just did, the third one? Really similar, right? David, it's the same problem, right? What we just did. Still you agree, right? So, how do you understand, right? Is this the same problem what we just did, like the third problem? You see, what is here given, like the radius, inner and outer? What is that? What is given, like the temperature, inner and outer, right, of the pipe surface? What else? The K value is given. Now, you know it's a cylinder, so you gotta use the cylindrical equation, right? And you have to apply all the boundary conditions. What are the boundary conditions again? Anyone? Steady state. 1D, equal to 0, right? Q dot equal to 0. So, and constant properties, right? So, what are we going to left with, Isaac? Just the first one, right? Just the first parameter, and you solve it. The solution, I said, like, you can skip it, okay? And your book, everybody have the book, right? I did emphasize at the beginning. If you just flip on the book, they have the derivation. Just like what I just said, okay? Exact same derivation they have over there, okay? So you flip it. If you'd like to, it's open book exam. If you'd like to put some more of the derivation, you do it from the book. That's fine. If you'd like to understand it, bring it to me. I'm gonna give you the understanding, or I can derive it for you, okay? As I said, even like 30 years or 25 years ago when I was a student, I used to do it. So it's a simple thing. As long as you have a good calc background, okay, you should be able to do it fairly easily. And I'm gonna help you. That part I don't wanna do it here. Don't wanna waste like 25 minutes of class time again today. Okay? So but the answer, I did show it to you, right? Harley, remember, me, you are not there. So there's this equation, and I was showing everyone what is the temperature distribution equation, how to find the value of the C1 and C2, those two constants, right? And once you have those values, how to plug it and get that temperature equation. Remember, Isaac, the final temperature equation? This question is asking, find that. So you all gotta do from the equation manual, write those lines, and I'll be happy. You understand? After applying those boundary conditions, after applying those assumptions and the boundary conditions, you write those things. And if you like to write more, I'll be happy if I'm gonna see that you'll write the derivations from the book. The book does the same. Once you have that first part done, what's the second part is asking? The Q. Did you remember I was showing the Q equation as well, right? I was showing how to find the Q equation. Just plug it here, plug the values, and you should be able to find the final value. How many of you are feeling confident with the first one now? All? Some are shaky. Those who are shaky, what is the question? How can I help? Anything? Anything that has a little bit confusion on you, you can say.
I understand it in theory, I just have to actually apply it.
So you just have to actually do it. Once you're gonna do it, you're gonna feel 100% confident, right?
Yeah.
You got the process. Let me explain again. What you're gonna do? You have the main equation, right? You're gonna apply those assumptions. You're gonna come up with a simple thing, right? And then you're gonna do like what? Are you supposed to do the derivation, right? I said like if you wanna do it, just get the book. Book does have the derivation. You write it over there. If you don't wanna do that, I'm fine with that. You just say like applying boundary condition at r equal to ri t1, at r equal to r0 t2, and then remember the equation that I wrote, t equal to what? Like c1 ln r plus c2, and then write that from the equation manual. And then next line like c1 equal to, remember I have the c1 value. After applying the boundary condition, you're gonna get that c1 and c2, right? So write those, and finally write the t equation. Okay, this is all in equation manual and all in books, right? The reason is given here instead of you applying only the equation, so you know what is going on in the background. Does it make sense? All right, Logan, you understand what I'm saying? Okay, once you have that, now everybody's feeling good. Okay, any more question? Any more question? Anybody have? Did you understand what I just said? Like,
Yeah.
So that's question number 1. And remember, what did I say? Emphasizing. Don't try to get a solution manual from anywhere. Try to do it by yourself to understand it. So, and then I have this. The second problem. This is problem number 2, 3, and 4. So I have the second problem. It says a plane wall of thickness 2L. So I have a plane wall. The thickness is 2L. Experience uniform thermal energy generation Q dot is given. As I said, even after the class time, I'll be still giving you the hints because this is what some of the students wants me to do. If you don't need that help, you can go away after the class time, okay? But I'll continue giving this whoever needs the help, okay? It's up to you. You have the liberty to go after the class time. All right. So this Q dot, and you know the video is gonna get recorded. So if you have other engagement, you can watch it later as well. So it says here, at x equal to plus minus 50. So what does it means really? It means x value is 0 here. So this is x equal plus 50 and this is x equal minus 50, right? Everyone understand the problem? All right, so that's the problem. It says by ambient fluid characteristics, the ambient fluid is flowing around here, right? It's T infinity. Okay, so the T infinity is 25. All right, if the steady state temperature distribution of the wall, so they gave you the temperature distribution T as A L square minus x square plus b, but the A is 10 degrees Celsius per meter square, B is 30 degrees Celsius. What is the thermal conductivity of the wall? So they are asking you to find the value of the K. That's a very interesting problem. What is the value of the convection? What's the value of the convection? And they are asking you the value of H is after. Okay, let's find the value of the K. How are we gonna find the value of the K? Any clue? You're gonna write the conduction equation like the heat equation for Cartesian coordinate, the big one. Everyone want to write the big equation right first. Okay, so then applying the assumptions, right? Once you're applying the assumptions, then you'll have this equation where you have this K over there. Okay, so if everything else is known, you should be able to find the K value, right? Right? Can you do that?
You can assume no energy generated.
Hmm?
You can assume no energy.
No, there is the energy
I
generation
know,
value
there's
they
a
gave you.
yeah.
You got.
I was thinking of what should be in the front. So the same thing.
What is the thermal conductivity of the wall? Did anyone start to solve it? Okay. Yeah, I hope the result is correct. But the technique is 100% correct. So you just come up with like the derivative. So you gotta do the derivative twice. So it's a little bit tricky. Let me help you. Okay. This one I feel like maybe I should be giving you a little bit more. Okay. So here you would like to start with. Okay, Matt, think this way. They are asking the value of the K, right? And they give you the value of the Q dot. So here's the clue for you or hint that you gotta use what? You gotta use the heat equation for Cartesian. Once you have the full equation, then you just apply those boundary conditions. What are those? The steady state, take out the right one. The one you're gonna take out the other two. You're gonna leave with only those two terms. One is the Q dot, another one is the x dependent term, right? And then here's the T equation given. So you're gonna apply the T equation up there on that differential equation, right? And you'll apply the derivative twice. Okay? And the T equation is given with all the values. Right? So that part is a little tricky. I'm going to show you a little bit, okay, how to do that derivation. And then once the Q is known, everything is known, only thing will be unknown is the K. As long as I found the K value is 50, you should be able to find the value of the K is 50. But, okay. Let me give you some more directions. So I'm saying you have this. Everybody is familiar with this equation. By now, everybody should memorize this, right? What are my assumptions here in this case? Isaac, what are my assumptions? Is the steady state one assumption? What else? 1D? Another assumptions? Right? 1D, right? It's just 1D. It's the x direction they're saying. They didn't say any other direction. And the constant property, right? K is constant. So this is gonna take out all this parameter and I'm gonna leave with only this. Okay. How many of you don't understand this? Everyone understand this? All right. So then what will be our next approach? It's become a, from partial, it became a ordinary, right? Because it's just 1D. So I'm gonna write it like, I'm gonna write it 1D. So d by dx, dt by dx. All right. Now, do I know the k equation? So I should be writing d by dx. What is my k equation? What is my k equation? A L square minus x square plus b. And don't get scared by seeing this equation because all of them you know except x, right? L you know, A you know, B you know, right? Matt, you know everything, right? Except the L, except the x. So this k will gonna come here. You have d by dx plus. Is it 12:30 already?
It's 12:19.
Okay. Thank you guys for paying that much of attention for a long, long time. It's really difficult to pay the attention for 2 hours a theory class like this, right? All right. Okay, I feel good. Like at least you guys are interested, right? So that clearly tells me. So now, how are gonna do that? How gonna do the derivative here?
First you gotta start with distributing the.
Yeah, distributing, and this constant derivative is 0, right? That will gonna go away right away. So you're gonna have d by dx, and then this a is constant, right? You can bring the a out, and you have
You have 2L plus 2X overall minus.
L square minus x square, right? Chelsea, you agree?
Yeah.
So this is constant as well, right? This will gonna go away as well. So then this is plus q dot equal to 0. Do you want me to solve any further, Matt? Or you're good? You can solve it from here. The derivative. So you have like this x squared. You see, Matt, what I'm saying? This L square is constant. It is gonna go away, right? So this x squared, we're gonna do the derivative, it will be 2x, right? So you have 2x, you're gonna do the derivative again for the 2x. 2x will gonna become only 2. So everything here will gonna be only 2, right? And that part I wanted to do it. If I'm gonna do it further, even though I say the result, then I'm giving you the whole thing, right? Matt, you need help? Yeah. Just work with your friend and then come to me if you are still struggling. I'm there to help, okay? So that's the first part. The second part, you can do it or no?
Isn't it technically -2?
This negative will gonna go
Yeah.
here.
That's what I thought. Okay.
So this, yeah, that way the k will be positive. All right. You want me to do any further? What is the value of the convection? What is the value of the convection?
I mean, once we have the
K. Once you have the
we
K,
have the K, that's,
then we can find the
yeah.
conduction. And the conduction equal to convection here. If there is no radiation, right?
Yeah.
Right? Isaac?
You just have to assume that radiation.
Think this way, Isaac. So see, if this is the block that we're talking, right? This block has the conduction happening. At the surface, convection and radiation can happen, right? If you can somehow find the conduction, conduction is what? You know the equation, right? It requires K value. Once you find the K from here, you can find the conduction, right? Once you know the conduction will be convection.
Especially if you stick with flux, you don't even have to worry about the area.
That's another thing, okay? If you do the flux, then don't worry about the area, right? And this is going to give you lead you to value of the H, right?
So, yeah, you still wind up with your H.
So you're doing double derivative.
All right. All right. So, yeah. Any question? Matt, do you want me to go any further? Or that is enough? Or 3 or 4? That's fine? David, it's fine? Can deal? Huh?
The equation manual changes.
Yep. So I'm gonna upload. Guys, after this class, I'll upload the equation manual and the video lecture both. Okay?
So just to specify in terms of the induction equation, our T2 and ones would be the alternate x's and the resulting of this equation, right?
Yeah, you can find those values. Yeah. You see,
So like that would be T2.
yeah, let me tell it to everyone. You
minus-
see, Chelsea pointed out a very important thing. You see, the temperature equations was given, right? So to find the conduction, you need the temperature. You use that temperature distribution equation to find the two temperatures. You understand? Or you can use this dt dx, okay, to find that value. Okay, dt dx. Can you do that? At the surface at x equal to 50, you're gonna find the conduction. Okay, Matt, that part is important. Please focus on that. What I'm saying here, if for the second part, okay, you see, at this surface, you want to find the conduction. Does it make sense? At this surface, if you find the conduction, which is this, by the way, I should be putting this as convection. The top one is convection, okay. So this conduction, to find that at this surface, okay, you know, at point to point it varies. You got to do this minus k dt dx at x equal to what? 50 millimeter. Do you understand? That should be your Q convection. That should be H T, that surface temperature. So that surface temperature is x equal to 50. Okay, minus T infinity. You understand? And from there you find the H value. You understand how to deal with that? It's tricky. This is not as straightforward as all. Very tricky. If I'm going to give you this kind of problem, it will be in the take-home part of the exam, okay? And the in-class are not going to have this kind of difficulty. Okay, I'll do my part, uploading those what I promised, okay? And then you do your part. Prepare well so you can do well in the exam.
I'll bug you if I have any further troubles with that.
No, yeah, bug me anytime, okay? Whenever you see me, this office hour just for reference only. It doesn't mean like you can't come another time.
And you respond to Teams messages too.
I do. I do. Unless my phone, my daughter is playing Roblox.
Naturally.
Yeah. Yeah.
Well, I know how it goes.
Yeah, exactly. Yeah. Where is my OBS?